The main goal of this lecture is to develop the basic rules of differentiation. These rules are particularly useful because they allow us to find derivatives without computing limits. We start with the power rule, which is used to find derivatives of power functions. Then we state the two linearity rules, which are the constant multiple rule and sum difference rule. The linearity rules can be combined with the power rule to differentiate any polynomial. To find derivatives of rational functions and other combinations of polynomials, trigonometric and irrational functions, we need the product rule and the quotient rule. Let's start with the simplest of all functions, the constant function, f of x equals c. According to the definition of the derivative of f is the limit as h approaches 0, f of x plus h minus f of x divided by h. Since f of x equals c for any x, f of x plus h is c and f of x is c. In the numerator we get c minus c, which is 0. Remember that h is approaching 0 but is never equal to 0. 0 divided by any number, no matter how small, gives 0. So the limit is 0. Therefore, the derivative of any constant is 0. This fact is obvious from the conceptual point of view, since the derivative is the rate of change and constants do not change. The derivative of any constant function is 0. We can also visualize the derivative as the slope of a tangent line to the graph of the function. Since the graph of a constant function is a horizontal line and the tangent line at any point coincides with it, the slope must be 0. Next, we look at the function f of x equals x. The graph of f is the straight line y equals x, which has slope 1. We would expect that the derivative of f is 1 at any point x. Let's check it using the definition of the derivative. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. Since f of x equals x, we obtain the limit at 0 of x plus h minus x over h. We see that x and negative x eliminate each other. So we have the limit of h over h. H divided by h is always 1, so the limit equals 1. Therefore, the derivative of x is 1. The next function on our list is x squared. We cannot guess the slope of the tangent line from the graph of x squared anymore. The slope is changing depending on the point on the parabola. To compute the derivative of x squared, we evaluate the limit as h approaching 0 of the difference quotient x plus h squared minus x squared divided by h. Expanding x plus h squared, we obtain x squared plus 2xh plus h squared minus x squared divided by h. Here we see that x squared and negative x squared eliminate each other. We can factor out h from the remaining terms, and then h in the numerator cancels with the h in the denominator. Since we do not have h in the denominator anymore, we can substitute 0 for h. What remains is 2x. Therefore, the derivative of x squared is 2x. Let's compute the derivative of x cubed. According to the definition, the derivative of x cubed is the limit as h approaches 0, x plus h cubed minus x cubed divided by h. Expanding x plus h cubed, we obtain x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed divided by h. Here we see that x cubed and negative x cubed eliminate each other. We can factor out h from the remaining terms, and then h in the numerator cancels with the h in the denominator. Since we do not have h in the denominator anymore, we can substitute 0 for h. This nullifies h squared and 3xh. What remains is 3x squared. Therefore, the derivative of x cubed is 3x squared. If we try to compute the derivative of x to the fourth, we would have to expand x plus h to the fourth and simplify. Otherwise, the computations are very similar. We would get that x to the fourth prime equals 4 times x cubed. Comparing the last three formulas, we see the pattern emerging. We can guess that for positive integer n, x to the n prime equals n x to the n minus 1. This turns out to be true and is referred to as the power rule. The derivative of x to the n equals n x to the n minus 1. You can think of the power rule as bringing down the exponent and subtracting 1 from the exponent. For example, the derivative of x to the power 17 is 17 times x to the power 17 minus 1, which is 17 x to the 16th. It can be proven that the power rule holds for all exponents, whether negative, fractional, or irrational. For example, let's find the derivative of 1 over x squared. First, we rewrite 1 over x squared as x to the power negative 2. Then we use the power rule. We bring negative 2 down and then subtract 1 from the exponent. We get negative 2 times x to the power negative 2 minus 1. Negative 2 minus 1 is negative 3. So we obtain negative 2 x to the negative 3. We can rewrite it as a fraction. Negative 2 divided by x cubed. The next example is to find the derivative of the square root of x. First, rewrite the square root of x as x to the 1/2. Then use the power rule. We bring down 1/2 and then subtract 1 from the exponent. We obtain 1/2 x to the negative 1/2. We simplify this to obtain 1 divided by 2 square root of x. Since the derivative of a square root comes up quite often, it is useful to memorize this expression to speed up the computations. The derivative of the square root of x equals 1 over 2 square root of x. Power rule works for irrational exponents in the same way. For instance, the derivative of x to the pi is pi x to the pi minus 1. Our last example is to compute the derivative of the cubic root of x squared. We rewrite it as x to the 2/3 prime. Then we use power rule. We bring 2/3 down and multiply it by x to the power of 2/3 minus 1. 2/3 minus 1 is negative 1/3. We rewrite this expression without the negative exponents and get 2 divided by 3 cubic root of x. Next, we state the linearity rules for the derivatives, which are analogous to the linearity laws for limits. Assume that f and g are differentiable functions. The sum difference rule states that the function f plus or minus g is differentiable and f plus or minus g prime equals f prime plus or minus g prime. So the derivative of a sum or difference of functions is the sum or difference of the derivatives. The constant multiple rule states that for any constant c, c times f is differentiable, and c times f prime equals c times f prime. So the derivative of a constant times a function is the constant times the derivative of the function. Combining these rules with the power rule, we are able to differentiate any polynomial. For example, to find the derivative of x cubed minus 5x plus 7, we use the sum difference rule to distribute differentiation to each term and constant multiple rule to factor out 5. Then we use power rule for x cubed to get 3x squared. The derivative of x is 1. Derivative of the constant 7 is 0. We obtain 3x squared minus 5. We will go over a couple more examples. Let's calculate f prime of x, where f of x is 1 over 2x squared plus 3 cubic root of x minus x to the power negative 3 halves. To find f prime of x, first we use the sum and constant multiple rules to distribute differentiation to each term. Then we use the power rule to find the derivative of each of the terms. The derivative of x to the negative 2 is negative 2 times x to the negative 3. The derivative of x to the 1/3 is 1/3 times x to the negative 2/3. And the derivative of x to the power 3 halves is 3 halves x to the 1 halves. We simplify. 1 half times negative 2 gives us negative 1. The second term, 3 times 1/3 is 1. And finally 3 halves stays. We get negative x to the negative 3 plus x to the negative 2/3 minus 3 halves x to the 1 half. We can stop here or rewrite this expression without negative exponents if we are asked to do so. We get negative 1 over x cubed plus 1 over cubic root of x squared minus 3 halves square root of x. The next example is to find f prime of 4, where f of x is 2x squared plus square root of x minus 1 divided by x. We need to find the derivative f prime of x first and then substitute 4 for x. Since we do not know how to compute the derivative of a quotient yet, we rewrite our expression first. by dividing each term in the numerator by the denominator x. We obtain 2x squared divided by x plus square root of x divided by x minus 1 divided by x. 2x squared over x gives us 2x. Square root of x over x gives x to the power 1/2 minus 1, and 1 over x is x to the negative 1. So the expression we get is 2x plus x to the negative 1/2 minus x to the negative 1. Now we can take derivative of f using sum, constant multiple, and power rules. F prime of x is the derivative of 2x plus x to the negative 1/2 minus x to the negative 1. We can distribute differentiation to each of the terms. We get 2 times x prime plus x to the negative 1/2 prime minus x to the negative 1 prime. Now we use power rule. The derivative of x is 1. The derivative of x to the negative 1/2 is negative 1/2 x to the negative 3/2. And the derivative of x to the negative 1 is negative x to the negative 2. Since we have negative 1 in front of the derivative, we obtain positive x to the negative 2. The last step is to substitute 4 for x in the derivative. F prime of 4 equals 2 minus 1/2 times 4 to the negative 3/2 plus 4 to the negative 2. Let's evaluate this expression. First notice that 4 to the negative 3/2 equals 1/8. Because 4 to the 1/2 is square root of 4 is 2. 2 cubed is 8. And since we had negative exponent, we get 1 over 8. Similarly, 4 to the negative 2 equals 1 over 4 squared equals 1 over 16. We get 2 minus 1/2 times 1/8 plus 1/16. 1/2 times 1/8 is 1/16, so at the end the answer is 2. It is not always the case with rational expressions that we can divide the numerator by the denominator, simplify, and use linearity of the derivatives. For instance, here, if we have x plus 1 in the denominator instead of x, we will not be able to divide and follow the same steps. To take derivatives of quotients and products of general functions, we use the quotient and the product rule. The product rule states that if f and g are differentiable, then f times g is differentiable, and the derivative of f times g of x is the derivative of f at x times g at x plus f of x times the derivative of g at x. The product rule can be proven by writing the difference quotient of f times g in a clever way and using limit laws. This proof can be found in any standard calculus book. Here we will concentrate on the applications. It may be helpful to remember the product rule in words. F times G prime equals first prime times second plus first times second prime. For example, let's find the derivative of 2x cubed times 4x minus 5. The first factor here is 2x cubed. The second is 4x minus 5. We apply the product rule. The derivative is first prime times second plus first times second prime. Now we take derivatives. The derivative of 2x cubed is 2 times 3 times x squared. We get 6x squared times the second 4x minus 5 plus 2x cubed times the derivative of 4x minus 5. The derivative of 4x is 4 because the derivative of x is 1. And the derivative of 5 is 0 because 5 is a constant. So the derivative of the second is 4. After simplifying this expression, we obtain 32x cubed minus 30x squared as our answer. It is important to remember that the derivative of the product is not equal to the product of the derivatives. To see this, take f of x equals x and g of x equals x squared. Then the product f times g equals x times x squared equals x cubed. And the derivative of the product f times g prime is x cubed prime is 3x squared according to the power rule. On the other hand, if we look at the product of the derivatives, f prime x times g prime x, we get x prime times x squared prime. The derivative of x is 1 and the derivative of x squared is 2x. So this equals 1 times 2x equals 2x. Obviously, 3x squared does not equal to 2x. To find the derivative of the product, always use product rule. We will look at 2 more examples of how the product rule is applied. First, we find the derivative of x squared sine x. The first factor of the product is x squared, and the second is sine x. By the product rule, the derivative is first prime times second plus first times second prime. Let's take derivatives. The derivative of x squared is 2x times sine x plus x squared times the derivative of sine x, which is cosine x. So the answer is 2x sine x plus x squared cosine x. The second example is to find the derivative of cosine x divided by x cubed. Again, since we do not know the quotient rule yet, we rewrite this expression as a product of x to the negative 3 and cosine x. Applying the product rule, we get first prime times the second plus first times second prime. Let's take derivatives. By the power rule, the derivative of x to the negative 3 is negative 3x to the negative 4. And we multiply it by cosine x plus x to the negative 3 times the derivative of cosine x, which is negative sine x. Rewriting this expression without negative exponents, we get the answer negative 3 cosine x divided by x to the 4th minus sine x divided by x cubed. This derivative also could be found using the quotient rule, which we now state. If f and g are differentiable, then f divided by g is differentiable for all x such that the denominator, g of x, is not 0, and the derivative of f divided by g equals the derivative of f times g minus f times the derivative of g divided by g squared. To remember the quotient rule, it is useful to say it in words. F over g prime equals top prime times bottom minus top times bottom prime divided by bottom squared. Our first example is to find the derivative of x squared divided by x plus 1. Here the top is x squared and the bottom is x plus 1. By the quotient rule, we get top prime times the bottom minus top times bottom prime divided by bottom squared. Now let's take the derivatives. Derivative of x squared is 2x times the bottom x plus 1 minus x squared times the derivative of x plus 1. The derivative of x is 1, the derivative of 1 is 0, so the derivative of x plus 1 is 1, and we divide by x plus 1 squared. After simplifying the expression in the numerator, we obtain x squared plus 1 divided by x plus 1 squared as our answer. The next example is to take the derivative of square root of x divided by x squared plus 5. Here the top is square root of x. The bottom is x squared plus 5. By the quotient rule, we get that the derivative is top prime times bottom minus top times bottom prime divided by the bottom squared. Now let's take the derivatives. The derivative of the square root of x is 1 over 2 square root of x. We computed the derivative of square root of x early and remember it for this kind of computations. We multiplied by the bottom, which is x squared plus 5, minus square root of x times the derivative of x squared plus 5. The derivative of x squared is 2x. The derivative of 5 is 0. So the derivative of x squared plus 5 is 2x. We divide it by the bottom squared, which is x squared plus 5 squared. To simplify, we can multiply the numerator and denominator by 2 square root of x. The expression we get is 5 minus 3x squared divided by 2 times radical x times x squared plus 5 squared. Knowing the derivatives of the sine and cosine functions, we can use the quotient rule to find the derivatives of the 4 other standard trigonometric functions. We computed the derivative of sine x to be cosine x and the derivative of cosine x to be negative sine x. Since tangent x equals sine x divided by cosine x, the derivative of tangent x is the derivative of the quotient of sine x and cosine x, which is, by the quotient rule, the derivative of sine times cosine minus sine times the derivative of cosine divided by the cosine x squared. The derivative of sine x is cosine x, and we multiplied by the cosine x, minus sine x times the derivative of cosine x, which is negative sine x, and the denominator is still cosine squared x. We simplify. Cosine x times cosine x is cosine squared x, and negative sine x times negative sine x is positive sine squared x. We obtain cosine squared x plus sine squared x in the numerator and still cosine squared x in the denominator. According to the Pythagorean theorem, cosine squared x plus sine squared x equals 1. And 1 divided by cosine squared x is secant squared x. Therefore, the derivative of tangent x is secant squared x. The derivatives of the remaining standard trigonometric functions could be found similarly using the quotient rule. We obtain that the derivative of the cotangent x is negative cosecant squared x. The derivative of secant x is secant x times tangent x. And the derivative of the cosecant x is negative cosecant x times cotangent x. To summarize, in this lecture we learned the 4 rules of differentiation: the sum difference rule, constant multiple rule, product rule, and quotient rule. We also computed the derivatives of basic functions. The derivative of any constant function is 0. The derivative of a power function x to the n is n x to the n minus 1. This is usually referred to as the power rule. Also now we know the derivatives of 6 trigonometric functions. All these formulas have to be memorized. This is the end of our lecture. Thank you.